or lab report. So a little introduction. Hello, my name is Daniel. So what was the purpose of this lab? So the purpose of this lab was to show simulated data versus real data and compare how they're similar and different, and see kind of the main differences between them. And we used a oscillating ball on a spring to show this, and this specific data used from the video of some guy who filmed it. So what models and principles of physics did we learn? Well, we used Hooke's law, which is the force of the spring equals negative K, which is the spring constant, times L minus L naught, where L is the stretched length and L naught is the unstretched length of the spring, times L hat, which is the unit vector of the spring. We also used F equals ma, which is Newton's second law. So those are both very important principles that we used to simulate data, to show motion, and to show how the spring interacted with the ball in this model. So why these principles? Well, we used these principles because we were using a spring, so it made sense to use Hooke's spring law, and we also were predicting motion, which is why we used F equals ma, which can be used to derive the prediction motion laws and predict motion and stuff. Okay, moving on. Sneak peek at the results. Well, we simulated motion and actual motion. The simulated motion and actual motion were very similar. It was very shocking how close these two were. So it showed that our simulations were pretty accurate, but I'll do more on this later. Okay, so our system versus surrounding and initial conditions. Well, our system was the ball and spring, and well, I guess the system was the ball, and the surroundings, the forces acting on the spring or on the ball, were the spring and gravity. A little bit of air resistance and drag as well. The initial conditions, the ball was launched from or dropped from zero velocity. So its initial conditions were equilibrium. But then quickly the spring was stretched. There wasn't pure equilibrium, but it was at rest, and gravity was acting a force on it, and the spring was acting a force on it as soon as it was let go. So here's some details of the experiment. The right has our x position versus time graph. The bottom is the x position versus time graph. And it shows the red one is going to be the experiment data graphed, and then the blue one is the model, kind of seeing what it should have looked like based on Hooke's law. But the red is just the tracker data that we've used from the video. So very similar. Here's some coding as well. We made sure to show all the forces that were acting on the object, and we used the energy principle to calculate how it moved and the forces that were acting on the object. We used GlowScript for this, and here are some screenshots of my code just for more proof. So, time to discuss. There were some differences from the predicted model versus the real model, and a lot of that could have been through human error. The tracker data wasn't perfect. We could only track one frame for every frame, and it moved differently in between those frames. Also, there is wind resistance and air resistance that we didn't account for. So that's also another thing that we have to keep in mind. And those were also why there's probably some potential errors. What if? So for your model system, is the energy principle satisfied? I would say yes. It definitely is, because we used in our GlowScript, we used how E initial would equal E final, and kind of how we use that energy principle of adding all the energies together, knowing that the energy of the system and surroundings does not change and stays constant. And then using your data, make two separate estimates of the oscillation period. So on the bottom left graph, it looks like one oscillation, I'd say roughly 0.08 seconds. You can see that a little more clear if you see the bottom of the graph, but trust me, it says 0.08. And then in the X position graph, it also, I'd say it says around 0.08 as well. So crazy how they're very similar, which makes sense, shows that it's a good oscillation. So that's about all I got. Thank you for watching.